So previously when we have m x double dot equals to k x equal to 0, what we do is we assume we multiply both sides by m invert. So we have x double dot plus m invert k x equal to 0. So we call these D matrix. And then we do eigenvalues, eigenvectors by the mode shape. But here for the mode analysis, instead of multiplying m inverts directly, we actually multiply 2m minus a half. You might be wondering why we're doing this. By doing so, we can guarantee that. So let me write it out. So what we're doing here is, instead of multiplying it by m invert directly, we just multiply on both sides x double dot plus k x equal to 0. So that's the trick we're doing. So it's different from the very first method. Over there, we just multiply m invert directly and get a D matrix. And then in here, after doing this, these give you identity matrix. You directly have x double dot. In the second part, we get a k tilt matrix. Your k tilt is just m minus half times k times another 1 minus half. So this k tilt is not the same as D. So why we're doing this? So the reason why we're doing this is for computational efficiency. So in this class, I think even for the final project, the degree of freedom is never go beyond 6 or never go beyond 10, I would say. So that means your M matrix and K, they're usually less than 10 by 10. So you can very easily calculate your D matrix in MATLAB. But in practice, sometimes your M and K can be really large. If you're doing FEA or something, these M can be 1 million by 1 million. That's going to give you a lot of trouble, especially when you want to use eigenfunction. Okay, so this K tilt actually is more efficient because one important property for this K tilt is it is symmetric. This symmetric property is important because if you look at the eigenvalues, an eigenvector, because if K is symmetric, there are two properties. The first property is P invert is equal to P transpose. The second property is your U1 dot product, I should say UI dot product UJ equals to 1, 0, if I equals to J, if I is not equal to J. So UI and UJ are normalized eigenvectors. All right. So that's the two major properties for the eigenvectors when K matrix is symmetric. The first one is very important. As I said, it's really hard to invert a matrix, but it's relatively easy to just take the transpose. You just switch the lines and columns. And then the second one is called orthogonal. Orthogonal property. So these can actually help you to simplify the calculation by quite a lot. All right, let me explain these using something here. So as I said, first of all, you convert your original matrix to m double dot plus k tilde x equal to 0. So after that, we just find out the eigenvalues and eigenvectors for k tilde. You have p, you have lambda equals to eigen k tilde. All right. So as I said, then what you can do is your x double dot equals to p times lambda times p invert x equal to 0. And then you can do and then you multiply both sides by p minus, and then this is gone, and then you can merge these two terms, and then form a new vector y, and then in y domain you have decoupled ODEs. That's something we already learned. So if you don't care why we're doing all of this, then let's directly go over these steps for you, and then we can talk about, we can discuss this using an example. So let's see, what's the best way to do it? All right, so let's directly use an example. I think that's the best way to do it. So first of all, the first step is calculate m minus a half. It's just 9 minus a half, 1 minus a half, 0, 0. That gives you 1 over 3, 0, 0, 1. All right, so the second step is we need to find the k tilde. Your k tilde is m minus half times k, m minus half. So just 1/3, 0, 0, 1. K is 27 minus 3, and 3. And then it's like this. And then when you do matrix multiplication, you just do row, column, summation, row, column, summation. And then eventually you can find out 3, 3, minus 1, minus 1. That's your k tilde. As you can see here, your k tilde is actually symmetric. And then the third step, we need to find lambda and ui's for k tilde. So remember, lambda and u, they're eigenvectors and eigenvalues. And then again, you can use EIG function, or you can calculate this by hand. Actually, we just did these. If you remember what we saw in the first example, we already calculated this. So lambda 1 will be 2, and lambda 2 will be 4. So then you can calculate your eigenvalues. Your U1 will be 1 and 1. That's your mode shape 1. So for convenience, we usually normalize it. So you divide the total vector by the norm of the vector. So that's how you do normalization. U2 is 1 minus 1. And then you have 1 over square root of 2. That is a mode shape number 2. All right. So after that, you construct a P matrix. Your P matrix, you just collect all your eigenvectors in columns. And then you would have 1 over square root of 2, 1 over square root of 2. As you can see here, the first column is U1. And then the second column will be U2. And then there's 1 over square root of 2 minus 1 over square root of 2. That's your P matrix. And then the fifth step is you need to construct a S matrix. Your S matrix will be M minus half P. And then let's copy and paste. It's 1/3, 0, 1, 0. And then your P matrix is 1, 1, 1 minus 1, 1 over square root of 2. Because 1 over square root of 2 is a constant, you can take it out. And then you can calculate your S matrix. This is a constant times 1/3, 1/3, 1 minus 1. So that's your S matrix. And then your S inverse is M half in P invert. And then when you do inversion for matrix multiplication, you have to reverse the order. So M 1 half. And then as I said before, because your K tilde is symmetric, we don't have to calculate invert. It's just P transpose. And then you can multiply this. P transpose is 1 minus 1, 1, 1. 1 over square root of 2. Because your P in this case is symmetric, so P transpose is itself. So you multiply it by M square root. It's just 3, 1, 0, 0. And then you can write these out is 1 over square root of 2, 3, 3, 1 minus 1. So what this S is doing is, the S is another transformation matrix. So when you see a transformation matrix, it's like, how should I say? It's like the movie Inception. Like it's kind of in your dreams. You're in a different level of dreams, and then you need something. You need something that makes sure that you know you're actually in dreams. So I think in the movie, they use a spindle or something else. So in our case, the reference or the things that are not changed when you do the transformation is eigenvectors. This is actually a reference. So that's why these eigenvectors are very important. So the only thing you can directly transform, like deliver, is eigenvectors. For example, in system 1 or in the X domain, I have these eigenvectors. Then in another domain, the eigenvectors won't change, but all the other stuff will change. Okay, so then you need, like for example, in here we have X domain. And then let's also name the other domain as R domain. So you have lambda here, you have U here, then you have the same eigenvectors and eigenvalues. But then for all the other stuff, like initial conditions, and solution vibration. So these stuff, they're different in two different domains. So what you can do is then you need some kind of like communication method to tell your code or your calculation that, okay, how can we communicate between these two different domains? So the communication is enabled by S. All right. So if you want to go from X domain to R domain, so whatever you have in R is S invert times X. If you want to go backwards, your X is S times R. So this S matrix is called a transformation matrix or coordinate transformation. If you see my announcement, I give you a very interesting link about eigenvalues. And then over there, they actually stretch a picture of a dog. And then you can see a lot of things were changed, but then there along one direction, all the pixels stay the same. So that direction is actually the eigenvector. Similarly here, so if you remember my very first example, if you have a coffee mug, you want to draw it on a paper. The easiest way is actually if you look from the top or from the bottom, so then you just need to draw a few circles and a square. And you can see over here, everything is simple. You can treat these as R domain. Over there, you can say everything is in X domain, and it's not, I think the relationship there is not as clear as the R domain. All right, so that's the power of eigenvector and coordinate transformation. So let's convert everything to R domain to see what's going to happen. So from X to R, your R is just S invert. So let's say previously you have your X dot plus K tilde times X equal to 0. Is that correct? No, I should put it a different way. Let's start from the very beginning. So in X domain, you have M X double dot plus KX equal to 0. So as I said, we want to look at the same system, but in R domain. In order to convert the X equation to R domain, what we need to do is we replace all the X by SR. So you have M S R double dot plus K S R equal to 0. Right? We just apply the coordinate transformation. That's the key. And then what is your S? Your S is M1 minus a half times P times R double dot plus K M1 half P R equal to 0. And then you can easily multiply both sides. And then you multiply both sides by M minus half. And then you have M minus half M minus half P plus K M minus half M minus half P R equal to 0. All right, so then let's recall a few definitions. So first of all, this is our K tilde. This becomes identity. So you have P R double dot plus K tilde P R equal to 0. And then you multiply both sides by P invert or P transpose, because P invert and P transpose, they're the same. So then you have P invert P lambda R double dot plus P invert K tilde P R equal to 0. So the first one becomes identity. The second one, that's just the method we use for matrix diagonalization, right? Equal to 0. So that's your equation in R domain. Then you see the benefits, right? Because lambda matrix is a diagonal matrix. That means in this R domain, all the equations are decoupled. If you want to write it out in R domain, you actually have n individual ODEs. So you have R1 double dot plus lambda 1 R1 equal to 0. You have your R1 initial condition and initial velocity. And then all the way to Rn double dot lambda n lambda Rn 0. You have initial conditions for that equation. So as I said, for each row, that's just free vibration of a single degree freedom system. You can easily solve that. So let's recall what we have. You have your Ri equals to a I sine omega I t plus 5I, right? That's just free vibration. And then remember, omega I is just the natural frequency, or which is the square root of that ith eigenvalue. And then AI and 5I are calculated from initial conditions. As I said, your initial conditions right now is in R domain, but then the problem description only give you initial positions and velocities in X domain. So you actually need to use this transformation method in order to get your R's naught. You need to use S invert X naught. In order to get the initial velocity, you have to do the same transformation. All right. Then let's go back to the original problem again. So we stopped at step 5. So then, if you look at it here, for step 6, you need to deliver information from X domain to R domain, right? The way you do it is just using an S transform, S matrix. The major information here is the information for initial velocity and position. All right. So eventually step 7, solve equations in R domain. As I said, in R domain, everything is decoupled. You don't have to do anything special. So in our case, in R domain, you need to solve 2 equations here. So let me see, 2 equations. You need to solve R1 double dot plus what's your first natural eigenvalue? I think one is 2, one is 4, okay. So this is 2R1 equal to 0. The second one is R2 plus 4R2 equal to 0. And then the initial condition R naught is S invert times 1, 0. So that is 1 over square root of 3, 3. And then your R velocity is S invert 0, 0. That gives you 0, 0. So this is the initial position for R1. This is the initial position for R2. This is initial velocity for R1. This is initial velocity for R2 dot. So that means you can plug this back in. You have R1 0 equals to 1, R2 0, R1 0 dot equal to 0. Right? So for each, then you, in our domain, the problem becomes a very simple free vibration problem. And then you just solve them individually. So then you have to go back to lecture number 3. So that's why I highlighted in here. But in this class, I already told you that when you calculate, when you calculate the invert tangent, you actually get 2 solutions. They are 180 degrees apart. If you use this method presented in the textbook, that's going to give you a big trouble, because then you have to select which phase lag is the correct one. So my suggestion is don't use this one. I'm going to present a new method here. So let's use a new one. So if you have a system m x double dot plus kx equal to 0, or x double dot plus omega n squared x equal to 0, initial position is x naught, initial velocity is v naught. The best way to solve it is you still assume that your xt is a sine omega nt plus phi. You still use the same format, but then it just gives you a different way to solve it. So your phi will still be invert tangent omega n x naught v naught, but then your a will be let me see, will be x naught divided by sine phi. If you use these 2 new methods to calculate your phase lag and amplitude, then you're fine. You don't have to choose which phi is correct. Just pick whatever you want. That should automatically handle the sign in your solution. So then let's use these methods to calculate your R solutions. For the first one, your omega 1 is square root of 2. And then your phi, we know that your R1 is some kind of amplitude times omega 1 t plus some phase lag. Okay, so that's your R1. So we first calculate phi 1, that's invert tangent omega 1 R initial position divided by initial velocity. Your omega is positive, initial position is positive. A positive number divided by 0, that gives you a positive infinite, which is half pi. And then your A1 is just our initial position divided by sine phi 1. So that's going to give you, oops, I think I copied it wrong. So when I copy it, it's actually 3 over square root of 2. I forgot to update the value. All right, so it give you 3 over square root of 2. So that's how you find your R1 solution. And for omega 2 equals to square root of 4 or 2, you can solve for R2. Similarly, your phi 2 is tangent invert omega 1, omega 2, R2 0, divided by R2 velocity. That's also positive half pi. And then your A2 will be the same, which is R2 initial position divided by sine phi 2. All right, so then you calculate everything in R domain. You can plug R1 and R2 back. and then construct a new solution, you would have 3 square root of 2 sine square root of 2 t plus half pi square root of 3 sine 2t plus half pi. If you don't like the half pi, you can actually convert it to cosine. So that's your solution in R domain. So the final step, we want solution in X domain. So we want to dump information from R to X. So your X, as I said, you have to go back to the coordinate transformation again. In order to go from R to X, we multiplied it by S. So what is your S? Your S is 1 over 3, 1 over 3, 1 minus 1, 1 over square root of 2. Your RT is just square root of 2 cosine. And then you can multiply this and then get the final solution. The final solution is cosine square root of 2t divided by half plus half cosine 2t, 3 halves cosine square root of t minus 3 half cosine 2t. So remember, the first row is the solution for x1. The second row is solution for x2. If you look very closely, you can see that for each solution, you have 2 parts. The first part oscillates at a frequency of square root of 2. The second part oscillates at a frequency of 2. So that means eventually a solution is still a summation of all the mode shapes. All right. That's how we solve these. That's the structure of modal analysis. Yeah, you might need some time to digest it. Let me know if you have any questions. You can send me emails after class. It's a lot of things to digest right now.